Here we go, we're looking at 10 questions all on resistance and resistivity. Let's get started. I'm hoping this won't last too long in comparison to the one on circuits anyway. Okay, so we'll start off with a simple one. We're looking at statements of Ohm's law. Generally, when we're looking at laws, they tend to be stated in a fairly complex way. Okay, so this first one here, the resistance of a conductor is constant. I would stay away from that one. Firstly, it's wrong. Okay, because we know that that conductors can change their temperature, their resistance, because of changes in temperature, and you'll see later that that's a key theme as well. Okay, so this one is very short and it's also wrong physics. The resistance of a conductor is not constant. Actually, the resistance will increase with temperature. Let's look at the next one. The current in a conductor is inversely proportional to the potential difference. Well, that's where I think we can call up our equation for current. It's V over R. You can see there actually that the current is directly proportional to V. If we double V, we double I. So therefore, this statement is also wrong. We then got two statements at the bottom, C and D, and they're very, very sort of similar ones. Okay. However, we've got a bit more detail in C. It was talking about whether the temperature is constant. Okay. We'll just skip over that one to D. The current in a conductor is proportional to the potential difference across it. Look at our equation. That is definitely true. It's directly proportional. However, we're missing that last detail about the temperature being constant. So actually, this last one is not correct because there's not enough information there. We then look back at our C and see the resistance of a conductor is constant provided that the temperature is constant. That is indeed the one we're going to go with here because it provides the fullest approximation of the situation that we're dealing with. We're going to now calculate a resistance. All we have to do here is remember our definition of resistance, which is that R is equal to V over I. And you can see there that I put on my graph a couple of lines that just allow us to identify the values of V and I here. V here is clearly 20, and I is clearly 2. So if I take 20 divided by 2, I get 10, and so the answer here is C. Now, where students have a problem here is the fact that they often mix up the X and the Y axes here. Okay, they forget that we are dealing with I on the Y-axis and V on the X. That's one point. That's where that 0.1 would come from. The 0 and the infinity is quite an interesting one. The 0 comes from the fact the gradient of this line. Okay, again, this is something that students often calculate, but they don't need to. You do not need to know the gradient here. And infinity is 1 over the gradient. And so again, this may be the case where a student has got a little bit confused with the meanings. So these zeros and infinites have been chosen for a very specific reason. Which of the following graphs shows the relationship between current and voltage for a filament lamp? Okay, let's just have a look at some of the sort of sillier values, sillier ideas. We look at B there, we've got a straight line, and so therefore that is an ohmic conductor. Now, the point here is that we're looking at a filament lamp, which is non-ohmic. Now, what we should be aware of is that the kinds of graphs we get for a filament lamp is D, and that's the answer here is D, but I want to talk about why that is. And I'm going to draw a quick line here. What you should be able to see is that initially our resistance is fairly constant. For low values of V, we've got a fairly constant value that's our ohmic conductor. However, very quickly V starts to depart from that ohmic conductor behavior, and that's the ohmic conductor behavior is shown in that blue dashed line there. What you should be able to see is that for a given current I, so if I take my cursor and just show you it here, my V values are greater than the I value for the ohmic case. In other words, for the same I, I've got a greater V. Well, resistance is V divided by I. If V has increased, so has R, and so therefore the resistance is increasing. And that's what we know happens in our filament lamps. As the temperature goes up, we know that the resistance gets higher, and that's due to the collision of our metal ions with the electrons as they try and flow through. Okay, there now follows a whole bunch of questions using our resistivity formulae. I'm going to build these up fairly gently. We're going to start with just the basic definition of resistance, or the equations we need, which is that R is equal to rho L over A. Here rho is the resistivity, L is the length, and A is the cross-sectional area. So for a given resistor Rx, it's going to have resistivity x, and then length x, area x, and etc. And those are combined in that way. Now what we want to do here is we want to determine the resistance of x divided by the resistance of y. Okay, and here I've just put my two equations from the top up there into that form. We've got rho x, Lx over Ax, and then we've got multiplied by the inverse of the resistance equation for y. Now I've highlighted in red here my rhos, that's my resistivity, because those two are the same material. If they're the same material, then they are going to have the same rho, and so therefore those two values are going to cancel out. So in the next line, we're going to get rid of the rhos because those were the same value. Those reds are disappearing. We're then going to look at Lx, Ly, Ay, and Ax, and have a look at what's in the information in the screen. Well, actually, we're told that x has a length which is twice that of resistor y, and that the area is twice that of our y. So actually I've replaced those two in the green, double Ly and double Ay, and you notice there that actually we've got 2 Ly Ay over 2 Ay Ly. That's the same thing. Okay, we've got A times B times C divided by A times C times B effectively, and so therefore actually the answer there is 1. Okay, so by doubling the length and doubling the area, so simultaneously making those two changes, actually the resistance of these two resistors is exactly the same. Somewhat boring conclusion, but a nicely worked out one as well. Okay. Now, here we've got a very similar situation. We've got two cylindrical copper wires. Again, they're held at the same temperature, so we don't have to worry about that. They've got the same resistivity. Okay, and W is twice as long and half the diameter. So again, we're going to start off from the point from the previous question, where we saw that as long as we've got wires of the same material, we can ignore the resistivity, as long as they're at the same temperature, I should say, and simply look at the ratios of the areas and the lengths in this way, L2A1 over A2L1. Okay. Now, we've known in the question already that 2 is double the length of 1, and so I can replace my L2 with 2L1, and you notice there I've got an L1 on the top and the bottom, and therefore they're going to cancel, so I'm left with 2A1 over A2. We then need to remember our relationship of area. Okay, we assume it's cylindrical, so it's got circular cross-section. Area is pi r squared. And so therefore, the area of 1, which has got, the area of 1 is going to be 4 times our area of 2. And the reason for that is because 2 has got half the diameter. If we half the diameter, we half the radius, and therefore squaring that brings out a factor of 4. So our area of the big wire is 4 times greater than the area of the thinner wire. And so therefore, we can put in our terms there. You can see on the top, I've got A2 on the top and A2 on the bottom, which leads to a factor of 8 because I'm multiplying 2 by 4. Therefore, a factor of 8. So remember, when we're changing the length, then that would be directly proportional. However, if we're changing the diameter or the radius, then what we do, we have to remember to square that difference. So if we're doubling it, then there's a factor of 4. If we're tripling it, it's a factor of 9, etc. Okay, we're going to keep going. We've now got a copper wire with a particular length and radius and resistance. And we want to know the radius of a copper wire with the same resistance but with different lengths. Okay, again, we're going to use R equal to rho L over A, and remembering that A is pi R squared. Okay, and so therefore, for the first wire, we've got length L, rho L over pi R squared. We then have a second wire, dash, okay, going a bit crazy with the colors here, sorry about that. Okay, we've got R dash is equal to the resistivity. Notice the resistivities here are the same because they've got the same material. Then we've got L dash divided by A dash. Again, I'm just going to substitute those guys in. Okay, where we've got my rho, my resistivity, and then we've got my length. And I know that my length dash is just half of the original length, and then we've got pi r dash squared, where r dash is the new radius. I can then set these guys equal to each other because the two values are equal. We've got rho and an L, that those guys are going to cancel. And we can ignore the pi as well. We've got 1 over 2 r dash squared is equal to 1 over r squared. We're going to flip these guys, invert them, and then square root. And we should see that r dash is going to be smaller than r by a factor of root 2. Here you should have a think about the fact that we did shorten the wire. And so to compensate for that shortening of the wire, we're going to make the wire thinner as well. So we expect r to decrease here, not to increase, in order to have the same resistance. Metal wire X with the length L and radius R has a resistance R, Y, and then we have the same resistance again. We've got the same kind of ideas here again. All right, again, we're going to equate their equations. This is rho L dash over pi R dash squared equal to rho L over pi R squared. That's just resistance equals resistance here. And we know that L dash is 4 times the length of our original one. Okay, and the reason we're highlighting that in red there is because we're going to cancel our L's. We're also going to cancel rho and pi, and we're left with 4 over r dash squared, 1 over r squared. And again, similarly, just similar to the previous problem, we're going to invert them, and then we're going to square root them. And we see here that r dash is double the radius of the original one. Again, you should think about this here. We're trying to maintain the same resistance value. If we make the wire longer to maintain the same resistance value, we then need to make the wire fatter, if you like, or have a greater resistance, a greater radius, sorry. And so therefore our answer fits in with that pattern. We're doubling the radius. A few more to go, folks. Okay, we've got 2 blocks with the same dimensions, but the same overall resistance again. Okay, and so therefore we can use our 2 values here. Again, they have the same material, so we're going to cancel our rho values. Okay, so we're left with Lx over Ax is equal to Ly over Ay, and therefore answer B here. This is quite a nice simple one compared to the previous ones. All right, we have a resistor of volume V. Notice this is V naught, the potential difference, length R and resistance, length L, sorry, and resistance R. We've got our resistance equation, always worthwhile starting with that. We've also got an equation for the volume. Volume is the area times the length. Sorry, that small L should be a big L, really, if I'm being consistent. Okay, I've rearranged my top equation there so that I can get an equation for the resistivity, because that's what we're being asked for in this equation. And I'm just going to substitute in my value for the volume here. Now, the way I've done this is I've multiplied the top by L and the bottom by L. L divided by L is 1, so I'm always allowed to do that. The top gets multiplied by L. You can see an A times L in there. And the bottom gets multiplied by L. That's L times L, so that's going to give me L squared. And so therefore, using the fact that V is equal to A times L, I've got RV over L squared, or VR over L squared, which is the same. Last one. Quite like this one. There's going to be a lot of colors in this one for you guys. Okay. First things first, we want to plot a straight line. Okay, and we're looking at different variables. Let's remind ourselves again. R equal to rho L over A. Okay, now in the question they're talking about the x-axis being either diameter or diameter squared, so it's worth remembering how we get diameter squared in there. Well, we've seen the equation A equal to pi r squared. That's also the same as writing pi d squared divided by 4. Okay, I'll leave that as an exercise for you to prove. It's a very simple one. Okay, we're going to chuck that into my equation now. We're going to substitute the red A's. Okay, and I'm left with an equation which is that R is equal to 4 times rho L over pi d squared. Now, what we then want to do is try and think about how we can plot something which will give us some sense here. Now, notice here we've got 1 over d squared in the equation here. So it's not really helpful to anybody because our x-axis has got to be either d squared or d. And so therefore what I've done is I've rearranged my equation to get d not on the denominator. Rearrange my equation there. I've got 1 over r is equal to pi over 4 rho L times d squared. Okay, so you're noticing here the answers A or C are going to be relevant here because I'm looking at d squared and not d. I'm then just going to do this. We wanted a straight line, and we want that straight line to be of the form y equal to mx plus c. Well, you notice here, we've got, on the left-hand side, we've got a variable, 1 over r, that's my y, is equal to pi over 4 rho L, that's my m, times x, which is my d squared. So actually, my answer here is answer C, which is 1 over r on the y-axis, and therefore and d squared on the x. Now notice here, we've got no c, we've got no plus, and that's because this line is going to go straight through the origin. Okay, it's a really nice exercise in rearranging your variables and making sure that they represent, they are representing their variables in a straight line form. Okay, a lot to go through there, guys, all very quick, as usual. Okay, I'm trying to make these as quick as possible so they don't take a long time. Please do take the time to watch them, and if you've got any questions, please let me know.